So for section 4.6, we're still talking about triangle congruence, but this time we're talking about CPCTC. And that is an abbreviation for the phrase corresponding parts of congruent triangles are congruent. So it can be useful to use as a justification in a proof after we have proven two triangles are congruent. So for example 1 here, it says to design a bridge across the canyon, you need to find the distance from A to B. Locate points C, D, and E as shown in the figure. If DE is 600 feet, what is AB? So we have to take a look at what we know. So the first thing that kind of caught my eye is the two 90-degree angles here. So angles D is congruent to angle B because they are both, that's given, they're both 90-degree angles there. And also given here is this is 500 and so is this. So those would be congruent because they're the same. So I'm going to label those with a tick mark. So DC is congruent to CB. That's also given. And looking here, these two angles would be congruent as well because they are vertical angles. So angle DCE is congruent to angle BCA because of they're vertical angles. And then if you look here, we have angle, then a side, and then an angle. So we can say that these two triangles, so triangle DCE is congruent to triangle BCA because of side, angle, no, sorry, messed that up, angle, side, angle. And we didn't talk about this part up here. DE is 600 feet. It says what is AB? So AB is this other side over here, which would be matching. DE is first and last here in this triangle, and BA is first and last in the other triangle. So those are the same sides. So if DE is 600, and we proved that these triangles are congruent, then AB has to be 600 as well. So segment AB equals 600, and we can do that because of that CPCTC. Corresponding parts of congruent triangles are congruent. So even though we didn't use that side length to prove the triangles congruent, now that we know they are, we can say that AB is 600 because of that CPCTC. All right, for example 2 here, we have this picture. It says given AB is congruent to DC, and that is shown there by the tick mark. So we're going to start off with that. So AB is congruent to DC because that's given. And angle ABC, so ABC, so this angle here is congruent to DCB, so this angle here. And that's given as well. We need to prove that angle A and angle D are congruent, so those top angles there. So if we look, we have this side and then this large angle. So we're talking about this triangle right here in red and the other triangle here that we're looking at here in purple. So what I noticed when I outlined those triangles is that they share a common side, which is BC. So segment BC is congruent to segment BC. So, because they're both on the using that same side. So remember, that's the reflexive property. That one we use quite a bit. Reflexive property of congruence. So now we have this side here is congruent. We have the two angles, and then we have the side at the bottom. So that is side, angle, side. So we can say that triangle ABC is congruent to triangle DCB because of side, angle, side. And then once we know that the two triangles are congruent, then the other corresponding parts, angle A and angle D, have to be congruent. So angle A is congruent to angle D because of that CPCTC. All right, example 3 here. We are given that EG is parallel to DF. So that is shown here by the little arrows. And we're also given that EG is congruent to DF. So that's the tick marks. Oops. And we need to prove that ED is parallel to GF. So we need to prove that the top and the bottom are parallel. And let's talk about these two. If they were parallel and they went on forever, they would look like this. And then this would be a transversal that's cutting that. So then we can say this angle is congruent to this angle because they are alternate interior. So they're on the inside of those parallel lines and they're on the opposite side of the transversal. So angle EGD is congruent to angle FDG because of that alternate interior angles theorem. I'm going to go ahead and get rid of my extended lines there. Also, something else that I notice is that the two triangles are sharing that common side of DG. So segment DG is congruent to segment DG, and there's that reflexive property again. If two shapes share a same side, then they are congruent. So then we have a side, we have an angle, and then we have another side. So we can say that these two triangles, EGD, is congruent to triangle FDG because of side, angle, side. Then, because we have proved these two triangles congruent, we can say, let me change the color here. This angle is congruent to this angle by that CPCTC because we've already proven the triangles are the same. So now all of the other corresponding parts are the same as well. So angle EDG is congruent to angle FGD because of CPCTC. And then if that is the case, let me change the color here. If these were our parallel lines now, and this was our transversal cutting them, then those angles would be congruent as well. So then we can say that those two lines, two segments, are parallel. And that is the opposite of alternate interior. So that's the converse. Remember, The converse is proving the angles first and then the lines. So converse of alternate interior angles theorem. So we prove the angles first and then the lines are parallel. If we know the lines are parallel first and then the angles, that's just the regular alternate interior angles theorem. So you have to remember that. All right, and our last example here is given these points, we have to prove that angle ABC is congruent to angle DEF. So step number one is to plot the points on a coordinate plane. And I did that for you. And then step two is to use the distance formula to find the lengths of the sides of each triangle. So we need to remember the distance formula, which looks like this. X2 minus x1 squared plus y2 minus y1 squared. So we have to find the lengths of each side. So we have to do this 6 different times here. So if I were looking at segment DF, I have to use the points for D and F. D would be number 1 and F would be number 2 just because that's the order they're listed up above. I'm just looking up here, right here. So X2 would be -1 minus X1 would be -4, so that would be actually +4 squared plus y from the second would be -2 minus y from the first would be -1, so that would turn into a +1 squared. So let me put DF here. -1 plus 4 is going to be 3. 3 squared is 9. -2 plus 1 is going to be a -1 squared, and that would be just 1. And if we add those together, we are going to get the square root of 10. So this is the square root of 10 right here. Then we're going to go FE. So again, I'm going to look up there and look at F and E. E is first, so it's going to be my number 1. And F would be number 2. So x out of the second is going to be a -1 minus x out of the first is 0. And then y out of the number 2 is -2 minus y out of the first is 2, and we have to square that. So -1 minus 0 is -1, squared is 1. -2 minus 2 is -4. -4 squared is going to be 16. So add those together. I'm going to get the square root of 17. That is not going to simplify. And then last on that triangle is ED or DE. And D is listed first up there, so that would be my point number 1. So y out of the second, or x out of the second, sorry, is 0 minus the first, -4, so that's going to be plus. And y out of the second is 2 minus y out of the first is a -1, so that's going to turn into a +1. 4 squared is 16, and 3 squared would give us 9. 16 plus 9 is 25, and square root of 25 is going to give us 5. So that is a 5 there. Now I'm looking at my time here. I'm running out of time, so I'm going to pause the video and I'm going to find the other 3 sides for us. After plugging the other 3 sides of the triangle in, you can see that they're all the same, so they're congruent sides. So the 2 triangles are congruent due to side, side, side theorem. But we have to prove that the angle ABC is congruent to angle DEF. And we can say that once the triangles are congruent, these 2 angles are congruent due to CPCTC.